Hello, my name's Kason Markley. I'm with the University of Illinois at Springfield, and today we're going to be learning how to use mass spectroscopy and infrared spectroscopy to analyze a structure. Now, we have the structure ready, so we're going to go ahead and start with mass spectroscopy. You want to keep in mind, so the first is that you want to identify your M plus peak. Now, what your M plus peak is going to tell you is what the molecular mass of your formula is. Secondly, you're going to want to identify your baseline peak. What your baseline peak is going to tell you is what fragments are necessary to identify your formula. Thirdly, you're going to want to try and use that information to identify some potential formulas for what your structure could be. Fourth, you wanted to figure out your degrees of unsaturation. Now, this uses an equation to determine how many hydrogens have been substituted out by other structures. And 5, you want to determine what a possible structure could be based on the formula and the degrees of unsaturation. Now here we have located a MS spectrum for our structure. And so on the y-axis you have your relative intensity, and on the x-axis you have your molecular mass. Now first off, you want to find your M plus peak. That's this one here. And our M plus value is about 111 based off the x-axis. And so you know that your molecular structure is going to be about 111 grams per mole. Secondly, you want to find your baseline peak, which is this one here. And what that's going to tell you is that anything to the left isn't going to be particularly helpful for finding your structure. What you're going to want to focus more on is those peaks to the right. Now sometimes these peaks can tell you whether or not you have halogens present. Sometimes the distance between them and your M plus peak can also tell you what possible formula units might be present in your structure. But for us, this one isn't going to be particularly helpful, so we're going to move on to step 3. You want to keep a few things in mind. So first off, you need your M plus value, which we found to be 111. And what's good about this is that since it's an odd number, there must be a nitrogen present. That odd number also tells us that there can't be any halogens. Now this is based off how many bonds nitrogen and halogens make. So what you want to do to start finding your formula is you want to subtract the molecular mass of one nitrogen from your structure's total molecular mass. So you take 111 minus the 14 and you get 97. So you know you have at least one nitrogen, but now you need to find how many carbons could possibly be in it. So to find the max number of carbons, you divide your new number by 12. So when you do that, you get about 8. Now, this is the max number of carbons present, but it's not necessarily the total. If you use 8, that means you only have one hydrogen left available based on your mass, and this is pretty unlikely. So what you want to do is you want to substitute one of your carbons in for 12 hydrogens. When you do that, it takes one carbon away from your formula and adds 12 hydrogens. And so instead of C8H1N, you now have C7H13N. So this is your new possible formula. And then you want to move on to step 4. Now in step 4, you're going to focus on your degrees of unsaturation. And as I mentioned earlier, this is going to tell you how many hydrogens have been displaced by other groups. Now, this is usually done through the formation of pi bonds or ring structures. That limits how many hydrogens can be bonded to the carbons involved. Now, to find your degrees of unsaturation, you use this equation, which is 2 times the number of carbons plus 2 plus the number of nitrogens minus the number of oxygens, minus the number of halogens, minus the number of hydrogens, all divided by 2. So if we insert the numbers from our formula, we'll get 2 times 7 plus 2 plus 1 minus 12 divided by 2. And that gets us a number of about 2.5. Now there's a small issue with that number. Pi bonds and ring structures each form 1 degree of saturation, which means that our number should be an integer. 2.5 is not. So, since we can't have half a degree of unsaturation, our formula must be slightly off. And so to fix that, what we can do is we can substitute carbons and hydrogens out for oxygens. In this case, we're going to try swapping them out for 2 of them. You're going to subtract 2 carbons and 8 hydrogens for a total molecular mass of 32, which is equal to 2 oxygens. And you're going to get a new formula of C5H5N1O2. Now when you recalculate your degrees of unsaturation, you're going to find that it now equals 3, which is good because this is an integer, and it's also very reasonable for our atomic weight. That means there's not too many bonds, but there might still be a ring structure. So with this, you can proceed to step 5. So at this point, you're on step 5, and you're going to try and find your structure. Only there's one slight problem. MS only finds you the molecular formula. And since formulas can be attributed to multiple isomers, you can't use the formula to determine your structure. What you need now is a little more information about your functional groups, and this is where IR spectroscopy is going to come into play. You're going to be measuring the absorbance of various different functional groups and bonds of infrared radiation. So on your y-axis, you'll find your transmittance, or how much is passing through it, and then you'll have your wave number on the bottom, which is found using the frequency absorbed by that particular bond or functional group. Now you have 5 zones that you're going to want to focus on. Now in zone 1, this is your hydrogen single bonds to anything that is not carbon. You're going to find this running between 3200 and 3700 wave numbers. Now in your second zone, this is going to be your carbon-hydrogen single bonds that have been sp3 hybridized. Now in this region, you're going to find it between 2700 and 3200 wave numbers. Zone 3 is your carbon-carbon triple bonds. You're going to find these between 2000 and 2300. Zone 4 is your carbon double bonded to oxygen, and this you're going to find between 1650 and 1850 wave numbers. And in Zone 5, you're going to find your carbon-oxygen bonds. And this is going to form in your 1480 to about 1680 wave numbers. This is also a region where you'll generally find aromatic rings as well. Now these 5 zones together form what is known as the diagnostic region, which is used to determine most of your structure. The other side, known as the fingerprint region, really isn't going to be particularly helpful for finding the general structure of your compound, and so we're not going to use it for this video. We're going to focus on this first peak right here. Now if you look at the graphic provided here, you'll see that various different functional groups can come up in zone 1, which is where this is located. So a smooth tongue would denote an alcohol. If it were 2 fangs, we'd have a primary amine. If it were bearded, we'd have a carboxylic acid. Or if it has 1 single fang, it could be a secondary amine or a terminal alkyne. Now if you look at this, it most closely resembles the primary amine because it's not bearded. It's only 1 point and it does not have a tongue. But we don't have enough information at this point to determine whether it's a secondary amine, amide, or a terminal alkyne. So for that, we need to look at the other. To help better analyze the rest of our IR spectra, I've gone ahead and zoomed in a little bit. And so we already noticed our first peak, which if you draw a line down to your x-axis, runs at about 3450 wave numbers, which is right in the middle of our zone 1. But like I said, we don't have enough information at this point to determine specifically what it is. So if we look at our second peak instead, we notice that this runs at about 3100 wave numbers. Now this is right in the middle of our carbon-hydrogen sp3 hybridized, or zone 2. So it's very likely we either have some alkane groups or methyl groups somewhere within our structure, but we won't know until we know the rest of them. Now if you look in our carbon-carbon triple bond region, you'll notice that we don't have many peaks in that area. A couple of small ones, but nothing particularly noticed, so it's highly unlikely that we have those in our structure. But if you look in our carbon-oxygen double bond region, or zone 4, you'll see this massive spike in absorbance. Now what this means is that it's very likely that we have multiple carbonyl groups within our structure. Now if you look here at this small little jutlet here, notice that this sticks out just past that into our COO and aromatics range, or zone 5. What this means is that we might have one of our oxygens either single bonded to a carbon, or it's possible that we have an aromatic ring somewhere within our structure. Now if we draw a line again at 1500, we notice that a lot of these larger peaks are after our fingerprint region. And so again, we're not going to use those because they won't really be necessary for our particular structure. What it tells us is some of the various ranges for which functional groups often appear on an IR spectrum. Now, if I draw in our line for our first peak, which was about 3450 wave numbers, we'll see that that passes right through the alcohols range. Now, normally, we could assume that this definitely points out an alcohol. However, recall that an alcohol has a tongue-shaped fashion, as shown by the graphic a couple of slides ago. So, it's unlikely that we have an alcohol. Also recall that we still have one nitrogen that we have not yet accounted for. And so if we go over one group, we'll see that there's the primary and secondary amine and amides, which is very close to our wave number and has the nitrogen that we have yet to account for. Spectroscopy to try and determine what a possible structure might be. So from mass spectroscopy, we learned that our probable formula was C5H5N1O2, and our degrees of unsaturation was 3. From infrared, we identified possible groups such as multiple carbonyls, an amide or amine group, an aromatic ring, and an sp3 hybridized carbon-hydrogen bond. Now, if we put those together, one probable result is that we have one aromatic ring as well as 2 carbonyl pi bonds, a primary or secondary amide and amine, and a methyl group. Attempting to draw it. Now, I used ChemSketch for this, but any program will really do. Now, what's really going to help is the fact of how few atoms of each element we have. That's really going to help determine where each one places so as to get the proper number. Now, we know to start off with that we have to have an aromatic ring, and we only have 5 carbons. So this means that we're most likely going to have a 5-carbon aromatic ring, such as the cyclopentene. We also know that we have 2 carbonyl groups, and since each of those requires a carbon, those are going to be bonded directly to our cyclopentene as shown. Now, we still have either a secondary amine or amide, as well as a methyl group to contend with. Now here, it's going to determine mainly on the number of carbons and net hydrogens. Now we already have all 5 carbons used, but methyl needs an additional carbon to function. Therefore, we need to substitute a nitrogen, or our amide group, in for one of our carbons. Now, I'm going to substitute it in for the one up top, and this is why. On the 2 highlighted, you would have a double bond to that nitrogen if it were placed in one of those positions. Nitrogen is not very fond of double bonds. It would rather form single or triple bonds. So it would rather stay up top where it can form single bonds to each of the carbons, as well as the hydrogen. Which still leaves your methyl group, but now you have the additional carbon you needed. Now you could place this, again, at the 2 regions shown below, or you could attach it in place of the hydrogen on the nitrogen. Now, I'm attaching it to the nitrogen for the reason of number of hydrogens. If you place it to one of the 2 bottom ones, you're going to have one too many hydrogens. But if you were to instead place it on the nitrogen, which eliminates that hydrogen and gives you 3 hydrogens with the carbon, you'll find that your total structure adds up to the proper molecular formula. So you'll see that you'll have 5 carbons, 5 hydrogens, 2 oxygens, and 1 nitrogen. Now this is just one possible arrangement. but based on our logic, it's a very probable one. And as you can see, is how you use mass spectroscopy and infrared spectroscopy to determine possible formulas and structures for a given compound.